Well, what do we know? Maybe. Okay, so we'll continue with the second lecture about unfolding. And just a refresh of your memory of what we discussed. There will be an overlap with the last part of the lecture because I usually have the last 5 minutes of the lecture with overlap, so we'll pick up from there. But just to recall, we're discussing about this generic problem where we decided it models steady-state heat propagation in a composite material with conductivity A epsilon given by this periodic function, conductivity some constant A1 in material 1, some constant A2 in material 2. Yeah, just to have this in the back of our minds. The periodicity of the function here you see the periodicity cell, so the whole domain is covered by this cell with material 1, material 2. Okay, and I want you to picture in your minds the fact that here, when we look at this problem, we look at the variational solution. So I'll write the variational solution instead of the PDE. So this is what we mean by a solution. For any psi in a space of test function, let's choose them smooth with compact support. Okay? So this is what we have in mind. So our problem is to pass to the limit. We understood exactly what we're looking for. The initial composite has a finite scale, epsilon 0. Because it's that small, we try to replace it with the most intuitive candidate, that is its limit when epsilon goes to 0. So we're trying to pass to the limit in such problems here. So pass to the limits in integrals involving sequences, products of sequences. Okay? So that's pretty much the nature of the story, and to some extent it was at a very more advanced level discussed by Professor Vaninathan in his lectures as well. Okay, so now for this we said we will use operatorial method. The unfolding operator was introduced, and how did we introduce it? Well, you remember we tessellated the whole space with an array of cells, epsilon y, and for every point in this space, well, normally one would associate its position vector to determine it, but because we want to take advantage of the microstructure given by the tessellation, we will associate with two pieces of information, that is the cell where it lives and where in the cell it lives, okay? And we said that this thing here, well, was given by epsilon times the integer part of x over epsilon with respect to y. If you have problems imaging this integer part, well, geometrically, if we assume y to be the unit cube, this comes actually being the integer part, or an integer in the Rn space with integer coordinates characterizing the cell. And here, this guy, where it is in the cell, was given by epsilon times the fractional part. Again, if you imagine y to be the unit cube, this is the classical fractional part, and that's what we had for x. So let's picture this geometry as well, and in this context, we define the unfolding operator for a function, measurable function, to be phi epsilon integer part of x over epsilon with respect to y plus epsilon y for x and y, x in the interior union of epsilon y cells translates, yeah? You remember, this is an important set, and Patricia made the case yesterday. So for any domain occupied by our composite, yeah, we consider the largest possible set of epsilon y cells. When epsilon gets small, whatever remains outside this set is negligible in a way, okay? So we define the unfolding of phi to be phi of epsilon times integer part of x over epsilon plus epsilon y for xy in this interior set. Y is always in the periodicity cell, and 0 otherwise, because the remaining part is negligible, so we can afford to eliminate it like that, okay? So this was our definition, and well, you had a homework. The first homework was to show that T epsilon phi converges to phi for smooth phi, continuous phi, for example, yeah? And you can have a very simple argument for this. It helps us to understand what's going on with the unfolding. So, although it was a homework, because you're not at home, so the concept of homework really loses meaning, so let's do it. So this is what we have. We look at the convergence in uniform norm. So for convergence in uniform norm, we measure the distance between the sequence elements and the potential limit in the norm of the respective topology, which is the supremum norm. So we need to look at absolute value of the differences. Now, just forget about anything fancier. Phi smooth, let's say phi is Lipschitz, just as an exercise, because Lipschitz functions have the property that they can be controlled by the distance between their arguments. So there will be some Lipschitz constant here, whatever, and times the difference between the arguments, okay? Something like that, okay? And if you use the formula for x here, okay, in here, and you get that this difference, the unfolding minus phi, will be less than L times here epsilon integer part of x over epsilon over y, respect to y plus epsilon y minus, and for x I use the definition that x is epsilon integer part plus epsilon fractional part. The minus comes from the minus in front. Okay, so now here immediately you see that what's left is epsilon y minus epsilon times fractional part of x over epsilon. So we have that whenever it is defined, T epsilon phi in x and y, this is this, minus phi of x is less than L times epsilon times absolute value of y minus x over epsilon, fractional part. This absolute value here, you can bound it by triangle inequality. Both y and fractional part are in the unit cube if we assume the periodicity cell to be the unit cube. So the whole thing is bounded by 2, this one, yeah? So this is less than 2L epsilon. And this here was obtained for every x in omega epsilon. So we can take the sup for every x in the interior set and every y in y. And that's it. That implies this, when epsilon goes to 0, omega, the interior set approaches the larger set, and we're done. So we have what this says is that with respect to the smooth functions, the unfolding doesn't do too much in the limit. By introducing the unfolding, you don't gain anything about the microstructure information if you apply it to smooth functions. Okay, but it's not the whole story, because we are interested to see how the unfolding acts on sequences which are strongly convergent and weakly convergent sequences. Okay, so and not necessarily smooth functions. Okay, because you remember that the idea is to apply unfolding to this problem. So at the end of the day, we don't know exactly how the unfolding will interact with this U epsilon solution of problems in a variational form which are not smooth. They have some derivatives in a weak sense. Anyway, they're not continuous or Lipschitz or in general. Okay, good. So let's move on with the next property. So we discussed before proving the most fundamental property of the unfolding operator, we can see immediately, and last time we showed that if we consider function, I'll stick to L2 as much as possible. L2, everybody familiar with what L2 space is? If you're not, raise your hand. I can tell you in a few words. Well, square integrable functions, just for the sake of conventions, this is the easiest space to work, and it has a Hilbert structure, and so we keep it here. If you consider an L2, last time we saw you extended by periodicity. Periodicity with period y to the whole space. And then you consider this sequence of highly oscillating function f epsilon defined by f of x over epsilon. And we showed last time that t epsilon of f epsilon restricted to omega is given by f of y in the interior set and 0 otherwise. Okay, we saw that last time. And more than that, this immediately, and this is a simple exercise I'd like you to try on your own. This implies immediately that the unfolding converges strongly in L2 of omega cross y to f as epsilon goes to 0, okay? So, so the strong convergence in the product space as epsilon goes to 0. I would like to take a look at the unfolding, because right now we define an operator which seems to have nothing to do with our problem. Yeah? And its very definition seems like out of the pocket. I hope you are with me, because I was there when I saw it first. It doesn't seem like something you would do without some hard thinking, like you would come up with. It's, so let's think about it and let's see if it makes sense. We need to make sense of this definition. The properties are simple, these two properties we discussed last time, but let's make sense of this definition. So what is this definition telling us? Okay? So, I'll forget the 0 part of the definition for the moment. So let's say we are with x, y in the interior set, and T epsilon takes a phi into phi of epsilon integer part plus epsilon y. So what do you observe? Well, one thing is that, in fact, for every x fixed, this is for x and y in the interior set, for every x fixed there, T epsilon is constant with respect to x in this cell. So, for example, we see immediately that for every x fixed in the interior set, the only information about x preserved in T epsilon is in which cell it resides. So that tells me that T epsilon of phi is constant on a fixed cell, epsilon p plus epsilon y, for example. Every cell of that interior set, on every cell on that interior set, this operator is constant with respect to x. Constant with respect to x. Let's further explore this. What does it mean? Well, I'm looking for x on this translated y cell, p epsilon plus epsilon y, let's say, for some p in the interval I epsilon. You remember this interval was those all integers corresponding to the epsilon y translates which are inside omega, okay? So I'm focusing on one tiny cell there. The minute I'm focusing on that cell, T epsilon for any function, T epsilon of phi in x and y on this cell is phi. What is the integer part of x over epsilon? Well, if you have x to be in the epsilon p plus epsilon y, the integer part of x over epsilon will be p, okay? So it's phi of epsilon p plus epsilon y. Okay, so there is no x dependence. T epsilon is constant on every cell of my microstructure with respect to epsilon, with respect to x. So constant with respect to x, it makes sense. Why does it make sense? Because I know that the minute I am in a cell, I don't care about this large variable x. The only thing x carries with it is which cell. So I need an operator, I need the machinery to bring me from phi of x. When you look at phi of x, x has in it the cell and where in the cell. I need a machinery to take me from phi of x to something which doesn't depend on, which records only the information about where, in which cell the x resides. So T epsilon phi does that. It takes me from phi, which blindly has both informations intertwined, and brings me to a black box, a machinery, an operator, which tells me that the minute I'm focusing on a cell, I lose x information. It disappears from the picture. Okay, I clear out the junk, in a word, because the only thing x carries interesting in it is in which cell. The next job is done by y, where in the cell, and that's what the operator does. Okay, so remember this. Okay. Okay, so now here we can do another trick. Well, since it's constant in the cell, then if I integrate with respect to x on the cell, just as an exercise, if I integrate with respect to x, the whole thing, so integrate with respect to x, it's constant, so it will be just the size of the cell, which is epsilon to the power n, times, well, if y is the unit cube, the measure of y will be 1, but I'll keep it there just for purpose of generality, times the value of, okay, so you get the picture of what this operator does. So if you start thinking, even if you don't know how to construct this operator, why is this important? Because if you deal with new geometries, if you deal with more complicated situations, you will be back to square one. How do I construct an operator to capture the microstructure? So you need to do this exercise. So pretend you don't know the definition now and say, okay, I'm looking at this problem, the generic problem. It has an x over epsilon. It has what is called a slow and a fast variable. How do I capture? And then you draw the geometry, and you see it's periodic. It's a bunch of cells. In each cell, material 1, material 2. How do I capture this information? In every x, I have two pieces of information. This and this. How do I separate them? Okay? Now, periodicity allows for these separations of scales, by the way. If you don't have periodicity, you have huge problems separating the scales. But periodicity allows it. And this is one way. So now you can imagine other structures and try challenge yourself. How do I construct an unfolding operator? So the unfolding operator is constructed so that it takes phi of x into an object which, when projected on a cell of periodicity, doesn't depend on x anymore. Okay, that's the main thing. Then, of course, this property is key for my problem. Why? Because eventually, maybe in the third lecture, we'll get to apply unfolding to this thing, so it will hit a of epsilon, which is a fast oscillating function. So I would like to have the possibility to pass to the limit there, to get rid of that. In the limit problem I'm dreaming of has no epsilon in it, has no fast oscillations, because I wanted to compute. Okay, so now let's move on. Again, what else? What do I do now? Well, again, we always look back to our problem. Always look back to what is the question. It's a variational problem on omega, involves integrals on omega. The unfolded operator, what does it do? Well, you see what does it do. The unfolded takes functions on omega and maps them on omega cross y. So somehow I need to be able to get from integrals on omega to integrals on omega cross y. Okay? So I need to be able to do that. If I don't have such an identity which takes integral from omega to integrals on omega cross y, I cannot apply my tool to that formulation. Okay? Now, we understand now why omega cross y appears. Because we have two scales in the problem. One lives in y, one lives in omega, and tells us kind of a very rough, large-scale information about which cell I am. But So we need omega cross y. But the problem is on omega only. Okay? So now we're developing our thoughts around it. So the unfolding is constant with respect to x on each cell. We have this, so let's move on. So let's now start and ask the main fundamental question. If I have an integral on omega of some function, doesn't matter what it is, let's say it's integrable, but or L2 in our minds. Can I transform it in some integral on the omega cross y of the unfolded? That's the idea, that's the natural idea. So now, I told you that I'm following a paper by the main authors of the method, published in 2008 in the Siam Journal of Applied Mathematics. You can find that paper. How many of you already have the paper? It's the introduction of unfolding method by Damlamian, Cioranescu, and Griso. But I want to advise you, the paper is written with heavy influence of Alain Damlamian, and he's a nonlinear analyst. It's not easy to read, and it's a paper coming from the authors. Usually the authors understand the problem very well, but they don't necessarily find the best way to convey the paper to a new audience, to convey the results. Why? Because some things are assumed without questions, you know? So for example, the unfolding identity. What you see there is the unfolding identity, an integral on omega cross y of the unfolded equal with an integral on omega. But that's not the natural way to proceed about things. Because if you see this thing, there's no way you can see that result unless somebody tells you, prove that result, then you can prove it. So the organic way the mind works, in my opinion, is this. You start from here, and you try to see if you can get to the product space somehow. So let's see. Well, what is this? Well, of course, I'm using now my intuition. My omega, the domain where the composite resides, is composed of two big sets. That's how I worked with all my definitions. The interior set, omega epsilon hat, and the residual set, very small and meaningless. Okay, so this is what I do first. Okay? Now, on the interior set, I have another property. The interior set is union of small epsilon y translates. So I can break the path here as well. So let's take it separately. So we'll keep this here. So now the interior set is the union. So it's an integral on a union for integer in that index set of epsilon y translates. Yeah, that's the definition of my interior set. Okay? And now I break the integral with the path again. So this will be a sum of integrals of phi on each of these with respect to y. Okay? Well, with respect to x. So, because we started with phi of x. Sometimes the devil is in the details. I mean, especially when you deal with these businesses with x and y, it's good to keep track of what's what. So this is where we are, okay? But what do I know? That the minute I'm focused on a cell, I know that the minute I'm focused on a cell, phi of epsilon p plus epsilon y, here, this is what I need to do a change of variable here, yeah? So I have what? I put x to be epsilon p plus epsilon y. Then dx will be epsilon to the n dy, okay? And so I have what? I have epsilon to the n integral on, now y belongs to y, phi of epsilon p plus epsilon y dy, okay? That's, okay? And so, here, I use the fact that on every cell, phi of epsilon p plus epsilon y is given by the average of the unfolded with respect to x on that cell, yeah? Because of observations we just made. So I just replace that here. The average. So I just use the fact that this equals with 1 over epsilon to the n measure y times the average of the unfolded, so the integral of the unfolded. So this will be this. So I have integral, so I replace phi, so I'll have integral with respect to y first, then integral of the unfolded on epsilon p plus epsilon y. This integral here is with respect to x, the first one. The second one was with respect to y. Okay? Now I switch the order of integration. Let's keep it here. Okay, here I have a cancellation. I switch the order of integration. I keep the 1 over measure of y, yeah, and I get this. Now I need to have dy dx, okay? And now, remember, now I have a sum. When P covers all those index, the index correspond to the epsilon y cells which are inside the interior set, okay? So this will be 1 over y. This sum of integrals on epsilon y translates is the integral on their union, yeah? So it's again the integral on omega epsilon hat, integral on y of t epsilon. So magically now we have t epsilon in the business, and that's it, okay? So because t epsilon is 0 outside this set, so it's, in fact, this is integral on omega, yeah? So it's, we obtain that the integral on omega of phi is integral on omega cross y, double integral, of t epsilon of phi. Well, not really, but we obtain that this is that. Okay, that integral on the interior set of phi is equal with the integral on the product set of t epsilon. So the result I would like you to keep in mind, fundamental result, is that integral, we'll write it like that, that's how it's written in the paper, that when we integrate t epsilon of phi, we have, of course, the integral on omega of phi. Now, basically, what we saw is that the integral on t epsilon was the integral on the interior set, but the integral on the interior set is the integral on omega minus this. So that's what we write here. Okay? This is a fundamental unfolding identity, but proved a little bit differently, and I hope I convinced you where it comes from and how it develops, okay? It's very intuitive. It's related to geometry. Why it's important to understand this like that? Because, again, if you want to apply the tool, you will deal with new geometries, and you will deal with the challenge yourself to come up with such a tool, okay? And the intuition process is similar, but, of course, every geometry has its own challenges. Right now, we are here. So it's not quite true that integrals on omega are integrals on the product space. We have this little bit of junk. But because gamma epsilon is small when epsilon goes to 0, if phi is good enough, L2, for example, will do Holder inequality. If you have a sequence, then you need to be a little bit careful. But anyway, we hope that in the limit, this thing will disappear. And in the limit, when epsilon goes to 0, integrals on omega will be, in fact, integrals on omega cross y. So pretty much, when epsilon is small, we can proceed and do these transformations of integral on omega to integrals on omega cross y. And let's see how now we have a dream. So let's state it. So I will just erase this part and state our hope. Okay. It's always to get back, it's good to get back to your main question and try to readdress your question based on what you learned so far. So now I'm having the equation there, the weak form, that's what I'm looking at. Want to pass to the limit here. Fine. But here now, if I am to believe that this junk doesn't matter, which kind of intuitively makes sense, but we'll see clearly why, then that integrals on omega of whatever, gets translated into integrals on omega cross y of t epsilon. So basically this will be transformed, this problem, I can transform it. It's an integral on omega. I transform it in integral on omega cross y of t epsilon applied to this. And here I can do the same if I want. But there's no reason why, because there's no epsilon here. Okay? At the moment. But, you know, let's leave it like that. We can always do that if we need it, the translation. So this, right now, with psi smooth, doesn't really care about epsilons. So this is my new formulation of the problem. Again, in an attempt to pass to the limit when epsilon goes small. But we know something about the operator. It's multiplicative. We showed that last time. So basically, this would be this times t epsilon of this times t epsilon of this, okay? Passing to the limit. Well, we already showed that t epsilon applied to smooth functions converge to the smooth function itself. So t epsilon of the gradient of psi. Psi is very smooth, has infinite many differentials. Infinite minus 1 is still infinite. No? So gradient will be a smooth. T epsilon of gradient will go to the gradient strongly. No problem there. Here, what is this? Well, this is t epsilon of a epsilon, and is similar to something like this. Yeah. So that goes also strongly to a of y. Yeah. So this goes strongly to a of y. This goes strongly to gradient of psi. So it seems like we are onto something. The only thing which remains would be to prove, to see what's going on with, would be that. Okay? T epsilon of gradients of functions which solve this problem. So right now, based on what we learned so far, skipping a little bit of rigorosity, like good applied mathematicians always do at the zero order step, we kind of see that the challenge, always is good to identify the blocking points of a problem, the challenges. The main challenge now will be to figure out limits of t epsilon of gradients of sequences, again, sequences which are solutions of this problem. Okay? If you know a little bit of PDE, you can kind of now see that maybe you get some bounds and those gradients maybe can be bounded, but we'll see later on. Right now, just referring strictly to properties of the unfolding, because I don't want to prove more than is necessary to pass to the limit. What properties do we need for the unfolding? So we have the unfolding identity, which helped us kind of to rephrase the problem. We have some convergence for smooth functions, which helped us here. We have the convergence of fast oscillation functions, which helps us there. So we need what now? To talk about what? Properties of the unfolding related to convergences of sequences. So that's what we will, so that hopefully we'll learn about this. Now, this is, well, the main point of the strategy. Okay. So far, so good? Everybody with me? Any thoughts? Any concerns at this point? Everybody's on board? Okay. Yeah. What's that? Yes, yes, yeah. You talk about this? Here? Yeah. Yeah, because you can get rid of this. Yes, but not only for smooth phi. Actually, you know, you can assume L2 if phi is constant now. But again, remember, we will deal with sequences. So for sequences, you need to be a little bit careful. But right now, I just said, let's assume that this will be dealt with. Okay? If we assume that this will disappear in the limit, then in the limit we'll have this equality. So thinking that we are closer to that, very close to that limit of epsilon goes to 0, we can assume that for a fixed epsilon small, we can do this. It's a little bit overarching, you know, but because look, this is not quite right. Here you'll have some extra well, it's, yeah, plus some extra. This will be exactly the equality, yeah? That is what remains of this after I unfold it in the product space, yeah? So this plus this equals this. That will be the equality. But I'm saying that this, because this is very small set, and here we will prove some nice properties, that will go away in the limit, okay? So, well, again, there is another thing. I believe in a lecture which covers the main points, but some of what we call in mathematics elementary points, which sometimes are not elementary at all, that is derivation starting from the definition. That's actually what elementary is, may be done by students in an attempt to better understand the material. So this means that I may leave some things out, which I think are not of major importance to understand the subject, but which I invite you to do carefully, because at the end of the day, everything needs to be done neat. But trust me that what is left out will be doable with very little background, okay? So, good. But anyway, so let's get back to our assumption here. So we'll just stick to that for a moment. Let's talk a little bit more about this, exactly back to your point. So we'll talk about properties of the unfolding with respect to sequences. So let me see. Did it answer the question? If phi is smooth. Yeah. Yeah, but only for phi smooth. Yeah, but what I proved here is for every phi integrable.
You have to work with sequences selection, not with just one function, right?
Well, yes, definitely you have to work with sequences.
Sequences of phi. It's not just one heterogeneity property for all phi.
No, but it is for all phi. The thing is that what he says is that in the limit, if I'm looking at this, then when epsilon goes to 0, this goes to phi. So there is no problem, because phi doesn't depend on y cancels, and equality. I'm saying that this proof is true in general for any integrable function. So when you look at sequences, which are not necessarily smooth, then you need a statement which is true for the class of all L2 functions, let's say, at least, okay? So what you prove by doing that limit argument is true only for smooth functions. Now, of course, you can go further and say, okay, I can do it for L2 functions by using density of smooth functions, but that's a diagonalization tricky argument. You need to be very careful there. But still, I'm telling you that when I apply a sequence depending on epsilon here, because that's true, I want to be true for sequences, then the limit proof doesn't work, okay? Yeah? Okay, sorry, I misunderstood your question at the beginning. But more talking is always good, so it helps us better understand. But actually, that's a good thought, Consider a sequence and see for what type of sequences you can actually prove this by your limit argument. Try this exercise. Okay, good. So let's see, unfolding. And limits. Okay, so that's so now before going there, we need to understand exactly what do we mean by the unfolding identity. So we'll make this convention. The convention will be that if in the limit this integral where phi can be sequenced depending on epsilon or not, if I have in the limit that this is going to 0, then I could say that I have the unfolding identity, and I'll just write it as an approximate equality. Okay? So this is our convention. Okay? And we'll see details when we get to apply. So now, unfolding and limits. Unfolding and limits. What type of limits? So before understanding what type of limits, we need to understand what is relevant in the context of our main problem. So how many of you have seen before this class this problem? Like any PDE? Raise your hand. Okay. Okay, so, but you all know L2 spaces. All of you know H1 spaces? Okay, so, well, so let's make a small digression, just enough to understand a little bit what we're talking about. So for every PDE, you can find a solution if you define carefully the space where you look for a solution. It's very cheap shot the mathematicians came up with. But trust me, any type of equation can have a solution if you properly define what a solution means, and that means properly define the space you're looking for. So if you look in a very, very large space, eventually you'll end up with a solution. So, but anyway, here, when we talk about the solution, we're looking to functions for which this thing is integrable. And these functions have a property that this function here, that is u epsilon, is my unknown. That's what I'm trying to solve for, okay? That gradient has some sort of integrability properties. So, and that being said, so we're looking for functions in L2 with the gradient in L2. This is my well, very unsophisticated assumption about the space of where I'm looking for a solution of this problem. The existence is guaranteed by many ways. One way is the Lax-Milgram. In here, there are many other ways. So there exists a solution with those properties satisfying this for every psi. So that, let's go with that. We're not going to prove Lax-Milgram, but let's say that it exists. Then you can get some bounds on the solution. Why bounds are necessary? As you saw, compactness is a huge issue. That is, in mathematics, if we are in good spaces, bounds give me the possibility to pass to the limit on subsequences. That's the key issue. So we want bounds, L2, bound the L2 norm, bound the H1 norm, bound the whatever norm, and hopefully that is a space which has the Eberle-Mullian property. That is a reflexive space and gives you, with every bound, some limit of a convergent subsequence. So here, our spaces are good. This is, well, what we mean when we say that u epsilon is in H1 is L2 with some derivative which is not smooth but is integrable, okay? Okay, then we want to get some bounds. Why do I want to get bounds? Again, want to pass to the limit. Next, because I need to know what to look for in discussing unfolding properties when applied to sequences. What type of limits? L2, L infinity, I don't know, uniform norm, what am I talking about? So I need to know where my solution lives and what type of limits I have. So let's do a little bit of math here. So everybody, if you believe that this has a solution, u epsilon, then you have room to play. What can you play with in this formulation? The degrees of freedom in this formulation are what? You're free to choose any psi you want to see particular properties of u epsilon, because this satisfies this for every psi. So you can choose psi whatever you want, as long as it's in this space. Okay. So remember, u epsilon was 0 on the boundary. And so, well, kind of it can be approximated by functions in this space. So you can assume that psi, you can find a sequence of psi which approximates your solution exactly. So one choice here could be exactly your solution. So if you choose psi to be your solution, you get what? You get that integral of a epsilon gradient u epsilon equals with integral f u epsilon. And now the PDE is transformed in the science of finding inequalities. Here, this term here is greater or equal, this term, I'll put like that. It's greater or equal than what? here you use the fact that A epsilon has two possible values, A1 or A2. So you can take the minimum of them. Let's assume that A1 is less than A2. So this is greater or equal than A1, gradient U epsilon square, okay? And so that means that this is less than equal than this. And here you use the Holder inequality, yeah? Well, we'll write it like that. Okay? And so now you have that A1, and this is the norm of the gradient in L2 squared, because the norm has a root here, so there is no root here. So less or equal than this, I call it a constant, because that's dependent on epsilon, times the norm in L2. It's just the norm, has a root. And now you use something, a trick, which is called the Poincaré inequality. And this trick says what? So you see, this trick says that if I have a solution, well, not necessarily for, but if I have a function in this space, again, my function is in H1 because it has a derivative in L2, yeah? But it has some other property, it's zero on the boundary. So in fact, this is how we kind of differentiate between functions in H1 with some arbitrary boundary value and functions in H1 which are zero on the boundary. So we put a zero there. And now for this space, we have that this function has the following property, that the gradient norm controls the with some constant depending on the set, controls the L2 norm, okay? For these functions. And so now you can apply it here in both ways and you get bounds. So let's apply it here. This is less than C times the gradient norm, okay? And now you divide by the norm of the gradient, and that leaves you that the norm of the gradient is bounded by some constant. So what we have here, we obtain that the norm of the gradient is bound by some constant, and of course, because of this, the norm of the function is bound by some constant, okay? And pretty much that means, without going into any other details, just roughly speaking, the norm of U epsilon in the space where it lives, H1, is bound by some constant. So, well, there are some things which are under the rug, technical things which I didn't cover, but just for you to know, so we have bounds. We have bounds in L2, we have bounds in H1. So bounds mean that I can extract convergent subsequences, okay? So, now, so I can have, I know that U epsilon has a weakly convergent, is weakly convergent on a subsequence to some functions U0 because of this bound in L2, weak in L2, okay? Of course, as epsilon goes to 0, yeah? Then we have here that the gradient of U epsilon weakly convergent to what you can show by using distributions, that it will be exactly to the gradient of the limit, okay? And these two together, using now a compactness result, compactness embedding, which is again a technical thing Patricia mentioned about, if you have these two together, they mean that you have a strong convergence in L2, and you can't improve this, weak convergence of the gradients. So this is where we are. So now going back to our unfolding, we need what? Well, we need to figure out how it applies to strongly convergent sequences in L2 and how it applies to weakly convergent sequences in L2, but not any sequences, gradients of sequences, okay? Gradient sequences. So this is where we are, okay. So getting back to the main road, the unfolding operator to, so we have this convention we'll talk about, so the unfolding operator to sequences. So we saw that the unfolding applied to a smooth function goes to a smooth function. Let's write this down. Now, the next step is to consider phi non-smooth, and we use the density. In L2. Here, we use triangle inequality and density. Now, last time I assigned it as a homework, cheating a bit, I hoped many of you will come and say I couldn't do that because I didn't have the tools to do it. But now you have the tools. So I'll show you how to do it. Well, I'm not going to do what Fermat did. You know the story, huh? That the proof can fit on the bottom of the board or the side of the page. So we'll just okay, so how do we prove this? Let's do this exercise together. So what do we need to prove when we talk about convergence? We need to prove the distance between the two things go to 0 as epsilon goes to 0. Distance in L2, because that's the space where I'm looking. So I'm looking at the distance, which is the norm of the difference. Okay? And now I'm using the fact that I can approximate L2 functions by smooth functions. I told you exactly why. It's like similar to Fourier series in concept, okay? So there exists phi smooth such that we have the norm of phi minus W in L2 is less than some epsilon for epsilon as small as possible, okay? Well, let's avoid the epsilon. Let's put a delta. Okay, for delta as small as possible. And now I'm doing the triangle inequality. Here is the usual trick, forcing phi into the business. Minus T epsilon of phi plus T epsilon of phi. Okay, plus phi, well, minus omega plus, so I do, and plus phi minus phi. Okay, let's look at it like that. Okay, so here is less or equal then, and I'll group them properly. Okay, plus T epsilon of phi minus phi, because I know that this is, this is good, small, and plus phi minus omega in L2. And now triangle inequality, okay? Triangle inequality will break it into 3 pieces, okay? And that's it. So here I am. T epsilon of omega minus T epsilon of phi is T epsilon of omega minus phi plus T epsilon of phi minus phi plus phi minus omega. Okay? Now, I know that this is as small as I want because phi is smooth. I know that this is as small as I want because of the density property. What I'm missing is this. But what do I know? I have this convention. Now, again, it can be applied to W minus phi. It can. It's constant function. So for any constant integrable function, well, constant independent of epsilon, I mean. For any functions which are integrable, I can apply. So this here, I have the property that, so this is, of course, in the product space always, yeah? So the whole thing is the product space, because that's what I'm talking about convergence here, yeah? So this is strong in L2 of the product space. And then here, when I break the whole thing, this is in the product space. This is in the product space. This is in the product space, but it doesn't depend on y. So I'll have a, well, measure of y here, okay? Just to be... Now, what do we do about this? This is the only thing which we don't know what to do about. Well, we use the fact that T epsilon verifies the unfolding identity. So I'm looking, and I look at this, at its norm, the L2 norm. Okay? But now, what is this? T epsilon times T epsilon, yeah? Okay? T epsilon of omega minus phi times T epsilon omega minus phi, okay? And this is T epsilon of omega minus phi squared because of the multiplicity property of the operator. Okay? And now I apply again the unfolding identity. Well, okay? But you need to be careful here. The remaining part here, this thing will make it so that the norms are comparable. What's important here is that when you look at the norm of T epsilon, the L2 norm of T epsilon phi is comparable to the L2 norm of phi for any phi. So the L2 norm of T epsilon applied to some function will be comparable, that is less or equal than the L2 norm of the function itself. So let's remember this property. The L2 norm of T epsilon applied to some function is greater or equal, some constant depending on the measure of y and whatnot, the norm of the function itself. This is the result obtained by properly manipulating the unfolding identity, okay? That's what we use here, so we have that T epsilon of W, the norm of T epsilon of W minus phi is less or equal than some constant times the norm of W minus phi, and this was small as well, so this could be small as well. So, so this is small, as small as you want, yeah? So all of them are small, that means that in the limit, this thing is small, so you're done, okay? So now, this is a property I would like you to remember. It's simple consequence of the unfolding identity, okay? So we saw that T epsilon takes smooth functions to smooth functions in the limit, also L2 functions in the L2 functions by a simple density argument. Let's move on to T epsilon applied to sequences, because that's the idea, okay? So, okay, we'll leave this here. And so far so good? Any questions at this point? Because now we enter a different area. So, so are we ready? Okay, good. So I have about half an hour.
Yes, you are the chairman, chair. You can take more time.
The chair does that? Well, when I was a student, the sport class, where I played a lot of soccer, came exactly after the math class. And my math teacher was the chair. He always loved to take extra time, and I hated him for that. So I'll try to stick to the plan. Although I loved math, you know, I loved soccer as well. Hmm? Okay, okay, yeah. But we'll see. I think it's fine. What's too much is not good. So, what about the case where I have a sequence which is strongly convergent in L2? What happens to the unfolding applied to this sequence? That's our main thing, okay? Let's do it together. We can do this together. Now, there are two ways to look at the limit question. One way is shooting in the dark. You have no idea how the limit looks like. Man, you need to show that sequence is Cauchy or something. You need to do something to show it converges. Put your hands on the limit, you know. But then, you can kind of guess what the limit is if you're an educated guess. And then you show that that's the limit. That's much simpler. So let's educated guess what the limit is. Not those of you which are familiar with the unfolding, because that's not an educated guess. That's an information for you. So let's, with the others, let's have this nice exercise. So what do you think the limit will be for a strong convergent sequence? Well, if you take the constant sequence, we are back to square one here. The constant sequence tells us something. So a strong convergence sequence, our educated guess should be T epsilon W epsilon goes to? Speak up. W, yeah. So this is an educated guess, of course we need to prove. Well, if it works for the constant sequence, but this is not a mathematical inference, by the way. One example doesn't prove the generality, but it helps your intuition to educate a guess. So let's say it goes strongly in L2 omega cross Y to W. Let's see if we can prove this, okay? The way to prove is classical. I need to show strong convergence. Now I am in friendly territory because I educated guess the limit. Of course, if the guess is wrong, I'm back to the beginning, but until then, we dream, you know? Many times when I work on a hard problem, I'm happy with an idea and then I quit for a day or two because I'm afraid the idea is wrong, you know? And it's such an enjoyable feeling to know that you have an idea which might work, and I just don't want to spoil the feeling, you know? So, but we don't have a day or two, so let's proceed. I'll erase this. Okay. So what do we do here? We have a norm, so the best way to play with norms is, you know, more of the same, more and more triangular inequality. So we need to take advantage of what? We have this piece of information that omega epsilon converges strongly to omega. So somehow, if I put an omega epsilon in here, might help. So let's squeeze in an omega epsilon minus omega epsilon plus omega epsilon minus omega. Well, I say omega, it's W, but okay. Now, okay, now triangle inequality by splitting in two will be good, but I don't know what to say about this, okay? So, not the best approach, no? So, something else, now your turn. What do you think I should squeeze in? I know something else about T epsilon of omega, so, no? So what if I do this? Would this work? I just use the only information I have. The omega epsilon strongly convergent to omega and T epsilon of omega strongly convergent to omega. So now this, if I do the triangle inequality here and here, this is less or equal than the norm of T epsilon now, this is W epsilon minus W, plus the norm of T epsilon of W minus W, okay? And now I should be good, no? This goes to 0 because I showed it there, and here, this is less or equal than some constant, the norm of W epsilon minus W, which goes to 0. So the whole thing goes to 0, yeah? So I have that for strongly convergent sequences, I'm done. So now this is what everybody kept repeating here in the context of our problem, here. If gradient will be strongly convergent, there's no homogenization theory. There's no difficulty, you see? You just pass to the limit. You have so many strong convergent sequences, they enjoy together, you know? So, but it's not. Okay? And so, it's not in general. So then, but it is weakly convergent, so now somehow, if I get to prove that T epsilon of gradient of U epsilon is weakly convergent to something, I can pass to the limit because weak, strong go together in the limit. When you have a product of two sequences, one is strongly convergent, the other is weak, you can pass to the limit in the integral of the product. And the limit will be the integral of the product of the limits, okay? So, but I didn't prove that. We're far away from that yet. But so now we kind of have a feeling. So strong convergent sequences in L2, again, there's something else hidden here. Why did we come up with the unfolding? To capture the multiscale information in a sequence, okay? But the multiscale information is not captured by the strong convergence in L2 at all. Okay? You see why? Because U epsilon solves a problem with fast oscillating coefficients, for example, and although that happens, it's strongly convergent in L2. Its unfolding will go to U0. There's no multiscale information captured in these limits. The unfolding is useless for strongly convergent sequences in a way if you want to capture multiscale information. But we know that multiscale information doesn't reside in the L2 convergences of sequences, but what will give you the multiscale information, the contribution of this multiscale, the fact that you're looking at a microstructure will be the limit of this, okay? So, let's see some other properties. Okay, these are, okay. Feel free to think about it, and if you have questions, now is the time to formulate more philosophical questions. We'll prove now a result, which is, because we looked at strong convergent sequences, yeah? So let's see the weak convergent sequences. So what happens if, well, this is the question. What about weak convergent sequences? W epsilon, well, let's use V epsilon because my W is like my omega, which is weak, so weak convergence in L2. What happened with the unfolder? This is your main homework. Well, to think about in your room. It's the fundamental question of this method. And you don't have gradients, so it's much simpler context. I want to see what you can come up with. Brainstorm. So we'll leave it here. But still in the weak convergence context, we ask ourselves the other way around. What happens if I have a weakly convergent sequence of this form, T epsilon, V epsilon, is weakly convergent in the L2 to some W hat, yeah? What if I have this? What does this tell me about V epsilon? Let's assume that I know that V epsilon is bounded. And because it's bounded, for example, you can immediately see, based on this relation, that T epsilon of V epsilon will be bounded, so then it will have a subsequence which was weakly convergent to something. Let's call it W hat. Again, it will be a function of X and Y. It's in the L2 of omega cross Y. Question is now, what does this tells me about V epsilon? That's the question, okay? Every time you try to prove something, you are in a very good position if you don't need to invent new theory. That is, if you start with what's given to you, with those assumptions, and by removing the makeup, simplifying, rewriting them, they will unfold your answer. It's again unfolding. Everything unfolds. So let's see if this is the case. This is my assumption. I have T epsilon of V epsilon weakly convergent to something. What does it mean to be weakly convergent? It means it converges in a product when multiplied with smooth functions, test functions, okay? So I have that this is, my information is equivalent to saying that T epsilon V epsilon multiplied by phi, smooth in the product space, converges to, okay? Well, let me replace phi by T epsilon phi because this is true for every phi. So what happens with this guy? Well, if I'm looking at this product here, I know its limit, but I also know that based on the unfolding inequality, this looks like this. Well, let me look at this. Okay. And this, well, right now I'm stipulating that it has this property. Is this true? That I can use the unfolding identity, which I erased, it was here, that I use the unfolding identity to products of this form, V epsilon phi. Remember, when could I use the fact that this equals with this? Remember, when this will go to 0, okay? And I challenge you to prove that. It's just a simple consequence of Holder inequality, or Cauchy-Schwarz for our French friends. Okay. So, since this is the case, I can use this. I can use the fact that the unfolded, that the T epsilon V epsilon phi is V epsilon times phi. Huh? And now, I pass the limit in both sides. The limit here is what? Well, this I know goes weakly to W hat. This I know goes strongly to phi. Yeah? Weak, strong, the limit can. So the right-hand side would be W hat times phi. Everybody with me? Yeah? That is the left-hand side here. The right-hand side is the limit when epsilon goes to 0. I just copy and address the limit, okay? And I can do this for any phi in the space of test functions. Smooth, okay? So what is the trick now? Phi doesn't depend on y, so this integral here is integral on omega, integral on y of w hat times phi. Phi gets out of this integral. Well, you have a 1 over y. And let's copy the right-hand side term. Okay? And so if you do the manipulation further, you see that phi gets out of this integral, so in fact it's like this. So pretty much we have that the left-hand side is integral on omega, the average on y of the limit w hat, and that's supposed to be the limit of products of the form v epsilon times phi. But this is the definition of weak limit of v epsilon. V epsilon, that means, since this is for every phi smooth, v epsilon converges weakly to this. So what this tells me about v epsilon is that v epsilon converges weakly to the average of the limit of the of w hat. Okay? Everybody sees that? It's just a manipulation of unfolding identity, and but now we remember the oscillating functions. Patricia said in her book that proof took 1 page, f of x over epsilon. So now 1 chapter. Well, okay, 1 chapter. Okay, so now we can show it. Well, you can say in a line, but this line comes after 1 chapter as well. But let us be happy with the achievement and say in a line. So again, I remind you, the oscillating sequence, you have this function extended to by periodicity. To Rn with period y. Yeah, and period cell y. Then we build a function, okay? for every x in Rn. Well, you cannot do for every x, but almost every, because L2 functions are defined up to a set of measures 0. But just for those of you which are interested in these details. So now we also showed at the beginning, last class and the last course, and I reminded you that when you look at this, I reminded you at the beginning of this session, we show that this is strongly convergent, no? T epsilon of f epsilon restricted to omega, strongly convergent in L2 omega cross y to f. Remember, we showed that. Strong convergence implies weak convergence, so therefore, we can use this result, and that tells us what is the limit of this sequence of highly oscillating functions. F epsilon would be converges weakly to the average of the limit. That is the average of f. In this case, in this particular case, the limit of T epsilon of f epsilon does depend on x. So this is the proof of that result, that oscillating test functions, and Raji mentioned as well, converge to a constant value weakly and not strongly unless the sequence is constant. So now, this is that result proved here with a simple argument. Okay. Let's see what other properties. Yes. So, well, maybe a short digression about this, although it's not needed. Yeah. Okay. One last comment about the relation between the unfolding and two-scale, which is, you saw two-scale convergence being presented as an alternative method to deal with periodic multi-scale problems. And now we will just make a comment about the relation between the unfolding and the two-scale. Okay, so remember what is the two-scale convergence? So we said that a sequence two-scale converge if, let's see, the test functions here well, I guess there are many test function spaces. I'll just say smooth functions. So I'll just keep it like that. If the integral of v epsilon phi of x over epsilon converges to the integral of v phi of x and y for any smooth enough function phi. Well, distribution in omega and L2 in y, but that's so this is the statement, okay? And if u is general, not the unit group, unit of the measure there. If y is the general cell. So this is a two-scale convergence, and now we want to see what happens what is the ratio between the unfolding and two-scale, and the claim is this, that they're equivalent. So that is, if v epsilon, I'll say here, two scales to v, then this is equivalent to T epsilon of V epsilon weakly converging to V, okay, in the unfolding sense. Okay, so how do you prove this? How do we prove this? Well, again, remember that the space of test functions here is phi smooth enough. So one possible is that phi is very smooth in omega, C0 infinity, and L2 in y, one possible space. Let's see how we prove this. How do you think we can prove this relation? Anybody? Let's see. Let's see if you have an educated guess. I'll buy you a coffee. So how can we proceed? Any proof. You know, you're trying to prove something. What tools do we have at our disposal so far? We have the definition of two-scale convergence, and we have the definition of the unfolded. Yeah. So here, the two-scale convergence. Let's do this implication. The other you'll do it. So let's prove the forward implication. So I know that this sequence two-scale converges. I start here. What do? I use the unfolding identity, and I get somewhere. And hopefully it will get me here. It screams for the unfolding identity because I know the limits should land on omega cross y, okay? So let's see, let's do it. And the other implication I would like you to think about it is just a similar thing. So this, well, I assume I can apply unfolding identity to this. Is it right to assume? Well, the V epsilon times phi is smooth in omega. So it has compact support with respect to x. No. So the product here is suitable so that I can infer that this product has the property that the integral on the vanishing set is small when epsilon goes to 0, okay? So try to fill in this detail, okay, if you want to be very, very precise, but let's assume we can do it. So then we end up with this. The unfolding identity tells us that this is the integral on the product space of T epsilon of the product, which is the product of T epsilon. And now I have T epsilon applied to these two-scale test functions. And we need to figure out what this is. And that's it, because here I know what's going on, yeah? Okay, so V epsilon, two-scale converge to V. Here I have a weak convergence of V epsilon, of T epsilon, V epsilon to V. So let's see what is this test function here. Okay, so T epsilon of phi by the definition would be what? Well, 0, or if I am inside the interior set, will be phi of, now we need to remember, T epsilon is the function computed in, the argument now is epsilon, integer part of x over epsilon plus epsilon y, so this is the function of x. This is like w of x. So the unfolded takes it in w of x. Okay? So I replace x with this thing, okay? Okay? So here I use periodicity for the test function in the two-scale. And here I use what? I use the smoothness. And if it's smooth, I can pass to the limit inside. This goes to x. And this is y. So this basically will go to phi of x and y. Okay? Okay. So that's the main idea. I would like you to fill in the gaps for this proof. But remember that the unfolding is equivalent to the two-scale. There are advantages and disadvantages to both methods. Again, but it's good to know both of them and some other methods. Each method is suitable for particular type of questions and not suitable for other questions. So let this be another piece of your homework. But don't forget about the main thing, which is more like philosophical conceptual. If you have a weakly convergent sequence in L2, what can you say about its unfolded? You will see that not too much, but I want to see what do you think you can say. Any questions? Any comments? Now, totally unrelated, but I want to share this with you, okay? This should freak you out. It's related to what Professor Vaninathan talked. And I really wanted him to give you this. Thank you. So it's just the right time, saved by the bell. No, but listen to this. It's a particularly striking example of his theory, but let's see if, and so I suggested to you And you think about it, if you can make sense of this. You'll see, it's a middle school problem. You have an equilateral triangle. Well, it's not equilateral in my drawing. So let's assume it's equilateral, okay? So size 1. Okay, everybody knows a little bit of geometry, I hope. So, so now let's take the midpoints and form the path. I'm going to form a sequence. This is the first term of the sequence, the sum of the lengths. So 1, 2, 3, 4. Each length, what is this? 1/2. This is, Thales' theorem is a half of this, so this is 1/2. This is 1/2, this is 1/2. So the first element of the sequence is the sum of 4 halves, which is 2. Yeah? And I keep forming the sequence. I take the middle points again. And I have now this plus 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 this, 8 times equal elements, each equal to a quarter. So 2 again. And I keep repeating this. I always get 2. I form this constant sequence. My question is this. This sequence is constant. I can go to infinity with 2. Why the limit is 1? Now this should be, and you know, what Professor Vaninathan showed holds the answer. But this is, I know, I was astounded when I saw it first time. In the college, I wanted to be friends with one professor. He hated my guts, and he said, you can be friends with me only when you answer this question. I had no choice, no chance to answer, to make sense of this back then. But it stayed with me. He died in the meantime. I could be friends now, but anyway. So I leave you with that, okay? Think about this. But it's related to what Professor Vaninathan talked. Okay, thank you very much.
So you completed your.
No, I have one more. Yes, I planned well, Nandam. I hope I have one more on Monday, no? You want to cut my lectures? You don't like... Let me close this because I want to tell you something which is we recorded.
Okay, thank you. Have coffee and come back. It's okay.
I need to close it because we are recording the thing we talked about.